because maybe we haven't finished it. But so formal charge, talked about formal charge. It's the difference between the number of valence electrons and the number of electrons that it owns in the Lewis structure. There's a couple different ways to word this, actually. So like formal charge can be number of valence electrons minus the non-bonding, minus half of the bonding. To put that even more simply, it's dots and lines. So the non-bonding electrons are the dots, right? Those are just lone pairs. And since we're considering half of any bonding electrons, that means for each bond, there's one electron. So we can just count the number of bonds. So in something like carbonate, for this oxygen, oxygen would have brought 6 electrons, minus 1, 2, 3, 4, 5, 6, 7. Makes it a -1. So when we're doing Lewis structures and doing formal charges on Lewis structures, there are sometimes, I guess depending on what we're looking at in a Lewis structure, there's different ways to consider it correct. Or I guess there's more correct and less correct. So carbonate actually is a good example of this. If I just do the Lewis structure for carbonate, we'd end up with something like, does that work out? Oh no, it wasn't carbonate, it was sulfate. 6, 6, 6, yeah, and then a 2- charge. Sulfate's a good example of this, okay? Because if you took Chem 20, you did Lewis structures, you didn't talk about formal charge, really the only goal there was to get octets for everything. And you might have learned about expanded octets and probably just a little bit. So like this Lewis structure, is there anything wrong with this Lewis structure from a Chem 20 perspective? Yeah, basically the octet rule is the only thing you looked at in Chem 20. And so all the oxygens have complete octets. The sulfur has an octet. Now, we were talking about formal charges. And so if we do formal charges for all of these, the oxygens, actually the idea of doing these in a different color, the oxygens are all -1. And the sulfur is going to be 1, 2, 3, 4, 5. So 6 minus 5 is going to be a +1. So we got formal charges on there. It's not too bad, right? It's only +1s. There's no like crazy +3s, +2s. But now that we've talked about formal charges and we've talked about expanded octets, we take a look at sulfur and say sulfur is in the 3rd row of the periodic table. And anything in the 3rd row of the periodic table or below, 3rd row of the periodic table and below, can technically have an expanded octet. And that's because at the 3rd n = 3, that d orbital is there. It's just high enough in energy that it doesn't get filled with any electrons yet. So when we're looking at this, oh, well, sulfur can actually have an expanded octet. So what happens if I form a double bond with sulfur? So if I take a pair of electrons from one of these oxygens, form a double bond, now it's going to change my calculations for formal charges. Since this oxygen now on the right will be 1, 2, 3, 4, 5, 6, that becomes 0. Eraser, please. And the sulfur will be 6 minus 1, 2, 3, 4, 5, 6. So that also becomes 0. So if we compare these, I'm going to switch this one back so that it doesn't have that double bond. It's -1, +1. Okay, so which one is better? The one with formal charges on everything, or this one that has fewer formal charges? Yeah, fewer formal charges. So if we can reduce the formal charges, it does mean that we have to use the expanded octet of sulfur, but that's okay as long as we're getting something else in return. So we go from 4 formal charges to just 2. Then you might say, why stop there? Why not just add another double bond? So if I add another double bond, it doesn't fit, make it smaller. So let's take one of these, take another oxygen, and create another bond there. So that becomes 0. But what does sulfur become? The formal charge becomes -1. Did I make my formal charges better by creating another double bond? I've got 2 -1s there. I've got 2 -1s on my previous one. The formal charges aren't better, I just moved them around. And I actually might say in this case that they're a little bit worse because oxygen's more electronegative than sulfur, so it'd be better if that -1 is on the oxygen. But mostly I want to point out that after this point, adding another double bond like this doesn't make the formal charges better, it just moves them around. Whereas the first one we did, I went from 4 overall formal charges, whoops, erase that, 4 overall formal charges, down to just 2. Anything beyond that doesn't actually make anything better. I think these two? I guess in this case, because we're talking about like the -1 is on the sulfur here, the -1 is on the oxygen here, it's better to have the -1 on the oxygen. But it also doesn't, I also don't really gain anything by adding a second double bond. So that's the difference between this one on the far right and the one in the middle. So the one in the middle has 1 double bond, the one on the far right has 2. So basically, if you get a structure like this, where you're like, I can add double bonds and it changes formal charges, only do it if it reduces the overall number of formal charges. All right, let's do another example. This is more with resonance. Lewis structure for an organic compound, CH3NO2, nitromethane. In organic molecules, there was one in the Lewis structures actually that had hydrogen, so CH3NH2. The hydrogens or the oxygens, they're going to be attached to the atom that comes before. So this will be carbon and then nitrogen. The carbon will have 3 hydrogens. The nitrogen will have 2 oxygens. The orientation of those doesn't matter all that much. And aside from, I think, the skeletal structure of this, they're basically the same as just other covalent Lewis structures. And so we need to count up the number of valence electrons. So that should be 24. Minus 1, 2, 3, 4, 5, 6 bonds worth of electrons. So that's minus 12. Leaving 12 electrons left over. And where's the best place to put those 12 electrons? Yeah, on the terminal atoms. So in this case, the only terminal atoms that we have that can take more are the oxygens. So 2, 4, 6, and go one at a time. Right. Remember to make as many octets as possible. 8, 10, 12. And now we can think about it from Chem 20 perspective. The very baseline check is, does everything have an octet? It does not. How do we fix the octet? Double bond. You'll probably be tempted to try and throw double bonds in before this step, but it really does help to put these electrons on the outside unless you know already what the molecule is supposed to look like. Now, formal charges. Hydrogens, they only have 1 valence electron, 1 bond, no formal charge for those. Carbon has 4 electrons, so 4 minus 1, 2, 3, 4, no formal charge there. Nitrogen will be 5 minus 1, 2, 3, 4, so that's a +1. And then my oxygen on top is going to be 6 minus 6, so that's 0, and then the one on the bottom is minus 1. So we're also told to include resonance structures. So for resonance structures, use an arrow, and you can really only have resonance structures with double bonds. So my resonance structure here is going to be between the oxygen on the on top having the double bond, oxygen on the bottom having a double bond. I can't have resonance structures where the fundamental connections of the molecule change. So if a hydrogen is in a different place, that's a different molecule. Only the bonds and the electrons change. Maybe I should say bond order. And then nitrogen's still +1. Oxygen on top, -1. Okay. So if we had more resonance structures, then we'd draw more resonance structures, but there's only 2. Good. Okay, so this is a weird. Free radicals are weird. They can only happen in ions or molecules with odd numbers of electrons. So when you have an odd number of electrons, that means it's not possible for all atoms to have an octet because there's going to be one odd electron somewhere. They tend to be unstable and reactive. So if we draw a Lewis structure for nitrogen monoxide, that's 5 electrons from nitrogen, 6 from oxygen. That's 11 total. So you might start out with, I should say, 11 minus 2, so that's 9. So 2, 4, 6, 8, 9. And this is a real thing that exists. I guess we could share, take one of those pairs, take one of these pairs. 2, 4, 6, 8. Nope, can only do 1. So the nitrogen's 1 electron short. And in this case, this will give me a formal charge of 0 for oxygen. And then for nitrogen, actually, this works out as 1, 2, 3, 4, 5. So it's also a 0. So I would put that lone electron on the nitrogen and not on the oxygen. Because if I do something like this, now my oxygen or my nitrogen is going to be -1 and the oxygen is going to be +1. So because that's has formal charges and this one doesn't have formal charges, then this would be the correct structure. So there's certain elements that we can expect this to possibly happen with. So actually, which of these would you expect to have a free radical? Why D? Why does it have an odd number of valence electrons? Yeah, chlorine has 7. No, yes, you said 7. But it's oxygen. If I put an even number with any other atom that has an even number of electrons, it's always even. But things like chlorine, so any of the halogens, they have 7. So unless there's 2 of them, or there's a charge, you have an odd number of electrons. The same thing is true for nitrogen. But in this case, I have 2 nitrogens, so that's 5 plus 5, which would give me 10 electrons from the nitrogen, plus 6 from the oxygen. You either have to have 2 odd-numbered atoms, or you have to have some sort of charge. CLO, let's see, so that's 13. Now, we haven't really talked about it. I've talked a little bit about electronegativity. So 13 minus 2, sorry, so we get 11. So we got 11 electrons to place. Generally, if you have the option, and especially in something where you know you're going to end up with a radical, start placing your electrons on the element that's more electronegative. And actually, between chlorine and oxygen here, it's pretty close. But chlorine, if I do 2, 4, 6, that means its formal charge is going to be 0. And then I do 8, 10, and then that last one would be 11. So that'll give me a formal charge of 0 on chlorine and a formal charge of 0 on oxygen. And again, just so you can see it, if I do this the other way around, then I get chlorine It'd be 7 minus 1, 2, 3, 4, 5, 6. So it'd be plus 1. And the oxygen would be 6 minus 7 minus 1. This is not as good. So you might have to play around a little bit to figure out where the best place for the radical is. Free radicals are definitely the weirdest situation that pops up. Incomplete octets aren't so bad. You just have to remember that boron and beryllium tend to have incomplete octets, and also aluminum, actually. Boron trifluoride. Lewis structure would be boron in the middle with 3 fluorines. Boron's got 3 electrons, plus 7 times 3. So 24 minus 6, 18. 8, 10, 12, 14, 16, 18. So that's actually where you stop. So you might think, oh, we need to make a double bond because boron's got an incomplete octet, but boron and beryllium are a couple of the few ones that just are okay with 6. Also in this situation, right now, do I have any formal charges that aren't 0? They're all 0. But if I make a double bond, so you take these electrons and put them here, now that fluorine on the left is going to be a positive 1. The boron in the middle is going to be negative 1. So by adding that double bond, I actually increase my number of formal charges, which I don't think will ever happen with other molecules. Forming a double bond always would decrease the number, or decrease the formal charges. Just as to satisfy my own interest. So this would be CH2O. So that would be before we actually go and make double bonds. So this would be the whole molecule. All of the electrons are in there. And we could do formal charges at this point and find that oxygen's going to be -1, carbon's going to be +1. And so when I make the double bond, which also completes carbon's octet, I shift that, so now oxygen -1, 2, 3, 4, 5, 6, so that would be 0. Now the carbon would be 4 minus 4, which is also 0. So we hadn't done formal charges like that before finishing a molecule, but in molecules where you do need to form that double bond, it also makes the formal charges better. Because it's small. Boron, beryllium, and actually aluminum will also. Ah, yes, and the expanded octets. So, like I said, period 3 and below can have expanded octets. Now, you only form an expanded octet if you've got leftover electrons, or if it makes the formal charges better. So we do like arsenic, trifluoride. That's going to be 21 plus 5. So it's 26. 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Oh, AS5, F5. Then it's just this. You might even want to bring this down. And then like SF6. Lots of dots. Like I mentioned before, this is because in that third row, n equals 3, one of the valid quantum number configurations includes d orbitals. So all of these electrons past the first 8 go into d orbitals. And then, is there an example of this? If you had like xenon, tetrafluoride, I think you end up with at least 2 pairs of electrons, and they just go on the xenon. Okay. Are there any questions about expanded octets? Nope. All right. We're going to skip these because I want to talk about polarity. Electronegativity and polarity, because you need this to talk about whether or not something is polar. So I think I've mentioned this, but electrons as dots is a really drastic oversimplification, especially since we just had an entire chapter about how electrons are waves and they're particles, and they exist in these super weird shapes around atoms. So we just call them dots, and it's a massive oversimplification, but it does have a lot of explanatory power. Right? We can use it to predict really the bond lengths in things that have resonance structures, why those are different. It's a powerful tool. But those electrons are not always shared equally. You think of the amount of the time that an electron spends around one atom or the other can be split. If it's perfectly covalent, perfectly even, then it's spending about 50% of the time around each. Most of the time, that's not the case. So polar covalent bonds are ones where the electron's not equally shared. So it's spending more than 50% of the time around one atom and less than 50% around the other. Hydrofluoric acid or hydrogen fluoride is a hydrogen monofluoride is one example of this. So these electrons, fluorine is a lot more electronegative, so the electron really spends most of its time around the fluorine and almost none of its time around the hydrogen. Electronegativity is actually defined based on fluorine. Fluorine is the most electronegative. It's so electronegative that we're just like, yeah, nope, that's the cap. That's the most electronegative anything can be. So fluorine up here at the top right of the periodic table is the most electronegative. And this is, for good reason, inversely related to atomic size. Right? Fluorine's really electronegative, partially because it has a high effective nuclear charge. Those electrons are really, or are filling a lot of the hole of the nucleus. There's minimal shielding there, meaning that fluorine is stronger at attracting and holding on to those electrons. As things get bigger, those electrons get farther and farther away from the nucleus. They feel less and less of the pull. And on the opposite end, those atoms are less able to attract electrons to themselves. It's just they're farther away. So down here all the way at the bottom left of the periodic table where we have the largest elements, we also have the lowest electronegativity. Sometimes called electropositivity. The highest electropositivity. And then because they just really don't react with anything, the noble gases aren't even included here. They're happy. They're not trying to attract electrons anymore anyway. Using general trend, how can we sort phosphorus, sodium, nitrogen, and aluminum? Which of those is the closest to fluorine? All right, so if we're looking at those four, nitrogen's really only 2 moves away from fluorine, because it'd be 1, 2, 3 moves. Anything with nitrogen first. No, so nitrogen's first there. It's the only one where nitrogen's first. Phosphorus comes next, because it's really just one more step away from fluorine. And then aluminum's the next closest, and sodium's the farthest away. So you can use this too for just any 2 elements, just saying, is one more electronegative than another? Which one's closer to fluorine? That's, again, general trend. You can actually calculate it using their relative electronegativity difference. So We sort these into basically 3 categories: pure covalent, polar covalent, and ionic bonds. And it depends on how unequally the electrons are shared. Pure covalent bond would be between 2 elements of the same type, nitrogen and nitrogen. Right? What's the difference in electronegativity between nitrogen and another nitrogen? 0. They're exactly the same. That would be a pure covalent bond, completely equally shared. If we take something that's unequally shared, hydrogen and fluorine, for example, we haven't looked at a table yet, but we have values for those. Fluorine's the most electronegative. Hydrogen would be pretty low electronegativity, so it'll fall somewhere in here where the electrons are mostly around fluorine. And then on the extreme end of that, maybe if we had sodium fluoride, we'd have a large enough electronegativity difference that we could actually just say those electrons are just transferred. They're not even being shared at all. Sodium loses 1, fluorine gains 1. And so this is more of a rule of thumb, this scale down here. It's more of a rule of thumb than it is an absolute, but it works with the electronegativities that we have on that chart. Actually, wait, we did look at this chart, which has them on there. So hydrogen and fluorine would be, this is like 2.1 and this is 4. So the difference between them is about 1.9. So that falls in the unequally shared region. Sodium and fluorine, sodium is 0.9. So 0.9 minus 4 give me a difference of 3.1, which is all the way into the ionic bond territory. And if I want you to actually calculate specific values, I'll give you a table that has the values on it. I don't expect you to memorize values for anything. Most of the time, you don't need to calculate a specific value because most of the time we're just interested in, is there a difference or are they the same? Or close enough to being the same. So dipole moment is another way we can measure these bond polarities rather than just using this relative electronegativity. So the dipole moment occurs whenever there's a separation of positive and negative charge. So dipole, literally meaning 2 poles, 2 ends of that, usually positive, negative charge. And then we can measure that as the distance times the charge magnitude. So measured in dBs. And again, we get the same relative scale. I don't know. I'm not going to ask you to calculate dipole moments. Again, we're more interested in what does this mean about the behavior of molecules? So if I have a molecule that has polar bonds, how does that behave differently from a molecule that doesn't? So I'm not going to pull up the table for this, except for maybe the last one. But we can take a guess just based on the periodic table. So if we got bonds forming between iodine and iodine, is that going to be nonpolar covalent or ionic? Nonpolar. What about cesium and bromine? Yeah, where's cesium on the periodic table? Far left on the bottom. So it's a metal. We can use previous knowledge here too. We've got a metal, and then we've got bromine, which is a non-metal, all the way over here. So we can make a pretty good guess at how big of an electronegativity difference is that going to be. Pretty big. Big enough to be ionic. Cesium bromide is an ionic compound. So that's another way that you can look at these and see, is it an ionic bond? Oh, it's a metal and a non-metal. So this would be an ionic bond. Now, phosphorus and oxygen, both nonmetals, but just based on where they are on the periodic table, take a guess at, are they going to be the same? So are they going to be nonpolar covalent? Are they the same distance from fluorine on the periodic table? No. Oxygen's closer than phosphorus. Yeah, so oxygen's closer to fluorine. Phosphorus is farther away. So from this, we can infer that phosphorus is probably going to be less electronegative. Oxygen's going to be more electronegative. So probably a polar covalent bond. Phosphorus is also a row lower. So we can go up and we can look at this. Phosphorus is 2.1, oxygen's 3.5. So phosphorus, 2.1, oxygen's 3.5. So difference between those is going to be about 1.4. I think anything greater than 0.4, polar covalent is greater than 0.4. And it would be less than 2. So there are some combinations on the periodic table that would give us something that's going to be nonpolar covalent between two different elements. It's always going to be, in this class at least, between two different nonmetals. I don't know how to turn this and make it not crooked, but carbon over here is 2.5. So other things with carbon that would be nonpolar covalent, phosphorus is right on the edge. Sulfur is the same. So sulfur and a carbon-sulfur bond is actually nonpolar. A selenium-carbon bond is nonpolar. Iodine-carbon bond is nonpolar. And carbon-bromine bond, it's like 0.3. It's very close. Yes. Yeah. So if it's really close, you'll have this so you can check. Most of the time I just want you to be able to say like fluorine and anything, oxygen and anything, chlorine and almost anything. So most of the time, if it's two different atom types, it's going to be polar covalent. I'll give you a chart that's easier to read than that one. This is taking longer than I thought it would. That's okay. Yeah, so in terms of polarity, so far just talking about polar bonds. Talk later about how those combine together to give us polar molecules. We also got to talk about bond energies and bond length. Bonds always require energy to break. The reason that bonds are formed is because there's a reduction in overall energy. So if you're going to separate two things and break a bond, you always have to put energy into that. And so our bond energies are defined based on the energy required to break 1 mole of the bond in the gas phase. A stronger bond takes more energy to break. So HCl bond, 431 kilojoules. Don't really have anything to compare that to. But breaking that bond, we could compare something else. Something that's going to be more than 431 kilojoules is going to be higher energy, or a stronger bond. Less energy be a weaker bond. So one of the things that we can do with this is combine it with Hess's law, and we can calculate bond energies for molecules based on individual bond energies. So these average bond energies are for example, a carbon-hydrogen bond in a bunch of different compounds on average is going to be 414 kilojoules. For some things it's going to be stronger, for other things it's going to be weaker, but we can have an average bond energy, and so we say for any carbon-hydrogen bond, we can make a guess at what that bond energy is. And so there are tables of these average bond energies where you'll have a single carbon-hydrogen bond. I guess you won't have a double or triple for carbon-hydrogen bonds, but you'll have a bunch of different values like this. So for nitrogen, for example, we got nitrogen with a single bond, nitrogen with a double bond, nitrogen with a triple bond. 163, 418, 946. That's one that you saw on the lab, the Lewis structure worksheet. So as the bond order increases, as I add more bonds there, that bond strength increases. So we can add all of those together to estimate enthalpy of a reaction. So it's always going to be bonds breaking, bonds forming. The bonds breaking are always going to be endothermic. I always have to put energy in to break bonds. And then when I form those new bonds, that's always going to be exothermic. So this equation here, right, there's no negative in this, but my bonds breaking is always going to be negative, bonds formed is always going to be positive. Even though the table is all positive. So as one example, If I wanted to add a chlorine, should have written this out. If I've got CH4 plus Cl2 forms CH3Cl plus HCl. And I want to know I want to estimate the enthalpy of that. Then I have to calculate breaking all of these bonds. That's going to require some energy. So I have to input energy. And then I have to make all of my new bonds. So in this case, we're just breaking the one hydrogen bond. And then we're reforming a chlorine bond, chlorine-carbon bond, and a hydrogen-chlorine bond. Let's see, the carbon-hydrogen bond is, do this. So carbon-hydrogen bond, I'm breaking one of those. So I'm going to have to put in 414 kilojoules for that one per mole. The chlorine bond is going to be 243 kilojoules to break. Those are positive because I'm putting energy into the system. Then to make the carbon-chlorine bond, carbon-chlorine bond, it's going to be a negative 339. And then the hydrogen-chlorine bond is going to be a negative 431. So if I add all of those together, 414 plus 243 plus a negative 339 plus a negative 431. You get a delta H of the reaction is negative 113 kilojoules per mole. Now this is just for breaking one of that type of bond and forming one of each type of bond. If I break more hydrogen bonds, then I have to multiply that by however many there are. So if we change this to CH4 plus Cl2 to CH2 Cl2 plus H2, now I would take my hydrogen-carbon bond breaking, so 2 times 414 plus just the 243 because it's just the one chlorine that's breaking. And then I'm forming plus 2 times negative 339 plus, and then I have to look up whatever hydrogen is. So for a negative 436. I think it's pretty straightforward. The only trick is remembering that this chart is always positive for everything. You have to make the bonds formed negative. And those are all based on average bond energies. So it'll probably be close to, if you actually used Hess's law and used standard enthalpies of formation, this will probably be close, but they'll probably be slightly different because we're using averages here, whereas bonds of formation is more precise based on actual experiments rather than a bunch of different types. Yeah, it's often said that energy is stored in chemical bonds. You might think like octane, gasoline, has a lot of stored energy, you might say, a lot of chemical potential energy. The potential is not actually in breaking those bonds. We don't get energy out by breaking bonds. We have to put energy in. The potential of those gasoline molecules comes from the fact that when recombined into carbon dioxide and water, that process releases a lot of energy. So it's the forming of the bonds that releases energy. All right, that's a great question. So reaction between hydrogen and oxygen to form water is highly exothermic. So which statement is true about the energies of the bonds that break and are formed? So you got the energy needed to break bonds required is greater than the energy released when new bonds form. Is it A? The energy to break bonds is greater, and you have to put more energy in than I get out. This is saying this is an exothermic reaction, meaning I get a lot of extra energy out. So A would be true for an endothermic reaction, but Not here where we have an exothermic. But B. Yeah, B is the opposite of the endo. So B has to be it. So it's for the exothermic reaction is where I break the bonds. When I form new bonds, I get more energy out than I needed to break the bonds. If the energy was the same, that means I wouldn't get any energy out. Everything put in also comes out, so it's just the same. More energy was released by forming the bonds. But you got to separate everything first. Separating things takes energy. Putting them back together releases energy. Right. For methanol, it says write a balanced equation for the combustion of gaseous methanol and use bond energies to calculate the enthalpy of combustion of methanol in kilojoules per mole. So CH3OH plus O2. Always need oxygen for combustion. And that's going to make H2O and CO2. We got to balance this. So we need 2. So that'll give me the 4 hydrogens that I need. Yeah, and then I just need 4 oxygens. Okay. I think that's balanced. Oh, I do have 5. This needs to be a 3 halves. So I multiply everything by 2. 8, 8, 8 of those. 2 carbons. There we go. Okay, so now to do this, we need to figure out first how many bonds am I breaking? Bonds of each type, really. So I've got carbon-hydrogen bonds, because the CH3, the carbon has 3 hydrogens on it. How many carbon-hydrogen bonds do I have in my products? None. So I need to break all of those carbon-hydrogen bonds. So that's going to be carbon-hydrogen bonds times 3. And actually, it's going to help to have at least a rough structure of this. Now, I don't need to break the carbon-oxygen bond because I've got a carbon-oxygen bond here. I've got at least 1 carbon-oxygen bond over there. But I do need to break an oxygen-hydrogen bond. What do you mean? Because there's hydrogen-oxygen bonds here? No. I think actually the easiest way to do this is instead of trying to figure out exactly which bonds you have to break, just break all the bonds and then form all of these bonds. Because when you do that, any of the ones that you didn't need to do will cancel each other out. Yeah, this is a good puzzle. All right, so let's just go ahead and break all the bonds. Tear it all down. So one of those, and then we need to break carbon or the oxygen bonds. Now what kind of bond is that between 2 oxygens? It is a pure covalent, but it's also a double bond. So oxygen double bonds, one of those, but then times 3 of those, and this is all times 2. I think I'm remembering now. I think last time I taught this, I just made a video for this because it's a lot. Annoying. I know that's too small for you guys to read. Okay, so let's do it like this instead, times 2. And this will be carbon-hydrogen bond is 414. Oxygen-hydrogen bond is 464. Carbon-oxygen bond is 360. And then the oxygen double bond is 498. And then for the bonds that we form, again, hydrogen-oxygen bonds times 2 times 4. This is why this is a lot. What type of bond is the carbon-oxygen bond? Not in terms of polarity. Is it a double bond, a single bond, or a triple bond? It's a double bond. And actually, both of them are double bonds. So there's 2 of those in that, and then I multiply that by 2, because there's 2 carbon dioxides. So hydrogen, oxygen, I use that one. That's now a negative 464. Carbon oxygen double bond is negative 1072. So then I need both of these sides added up. On the left, in my reactants, I need to put in a total of 5,626 kilojoules, plus whatever I get on the right. Yeah, hold on. I'll go back over this. So right now that's per 2 moles of. Okay. So where did I get all these numbers? In a way, you do need to have the Lewis structure for some of these things. Methanol in particular is one that's not super straightforward, because how are all of these things connected? Well, you could figure it out, but the hydrogens are all attached to the carbon because they're written right after the hydrogen. We've done these. The hydrogens are next to the carbon, so it's 3 hydrogens attached to the carbon. The oxygen is attached to the carbon. The hydrogen here is attached to the carbon. Would I give you methanol or something more complicated as an organic molecule on a test of any kind? No. Not without giving you a structure. There's too many steps here, because you need a Lewis structure for this. Also, you need to know that this has a double bond. You could know that because we've done a bunch of Lewis structures, but also, yeah, you got to know that's a double bond. Or that if it was N2, that would be nitrogen triple bond. Same thing with carbon dioxide. I've got the methanol there. This is going to be, right, that's the Lewis structure for oxygen. Water is probably the most straightforward out of all of these. Carbon has 2 double bonds to oxygens, which again, they're Lewis structures that we've seen, but I recognize that it's a lot. Okay. Now, when you're going through this, I was looking up all of the values, these numbers, the 414, the 464, the 360, those all came from the chart. And so that's why first I set out, okay, how many of what types of bonds do I need to break? When you have all the Lewis structures, it's a lot easier. Just write this one above also. All right, so I've got, for this first group, I have a carbon-hydrogen bond and then another carbon-hydrogen bond. So that's why I've got carbon-hydrogen times 3. Now, eventually I came back and I added this coefficient of 2. In retrospect, I probably shouldn't have multiplied the whole thing by 2 and just left this as 1 and left this as 3 halves, which feels weird, but again, we've seen delta H equations where it does that. But if you're just counting all the bonds, I've got 2 methanols, so the CH bonds, I've got 3 of those. I got to multiply it by both the methanols. Then this is the amount of energy that it takes to break 1 carbon-hydrogen bond. And again, you just look that up on the chart. So carbon-hydrogen is up here. That's the 414. Then for the other reactant here, it's the oxygen. Now, I know that the oxygen is a double bond, but you might not, which is why you need the Lewis structure. Then I can say, okay, that's oxygen double bond. I only have 1 of those in my oxygen molecule, but I've got 3 oxygens, so I have to multiply by 1. then multiply by the 3 oxygens, then multiply again by a value I looked up on the table. So basically just counting for each of these bonds, I need to break them, how much energy is going to take to break all of those. And those values are all positive, because that's energy that I have to spend to make those bonds break. On the other side, it's way simpler. We've got hydrogen-oxygen bonds. Again, you need a Lewis structure for water. Or maybe you don't, because hydrogen only ever forms one bond. But then in my water molecule, this one water molecule has 2 hydrogen bonds. So hydrogen-oxygen bond times 2. Then I've got 4 waters, so I multiply by 4. And then why is this number negative? Because we're forming bonds. Values again on the table, there's no negative values here. So if I'm looking at the hydrogen-oxygen, positive 464, that's to break a bond. Negative 464 is to form a bond. And then for the carbon monoxide, again, 2 carbon-oxygen double bonds. So carbon-oxygen double bond times 2 carbon dioxides times the bond energy to break or to form 1 carbon-oxygen double bond. And then I just did all of this multiplication and added those together, and that gave me negative 8,000. Do all this multiplication and add those together, and it gives me 5,626. Adding those together gives me negative 2,374. And then the last divide 2 is because methanol, there's 2 methanol, but I want it per 1 mole of methanol. So I could have skipped all of these multiplied by 2's. Clear as mud? Yeah. Multiply a bunch of numbers, then add some of them. Who am I? What is this place? Making a mental note to myself to just take that slide out. Do something way shorter than that, because that problem in itself is just too long. Okay, bond lengths. The simplest way to look at this, triple bond's the shortest, double bond's longer, single bond's longer. That also corresponds with the energy. So triple bond's shorter than a double bond. It's also stronger than a double bond. Why? Why would a triple bond be stronger? Yes, because 3 sticks, when held together, are harder to break than 1 stick. I joke, but that's it. But there's more being shared between those 2 carbons, right? They've got 6 electrons invested together in that bond. If that bond breaks, they lose 3 electrons each. So there's more invested there. It's a stronger bond. And that's also why the bond length is closer, because they're sharing more, so they have to be closer in order to share all of those electrons. So average bond lengths, we could even compare, I bet if we laid the bond energies next to these, we would see that most of the time shorter bonds are stronger, longer bonds are weaker. Like the previous slide said, there are exceptions. Oh wow, I'm surprised there's not anything in here about bond order. But, huh? Bond order is so easy. It's, yeah, the number of bonds divided by the number of resonance structures. I feel like we already had this slide. I think I mentioned it, but we didn't really talk about it because it's fairly complicated. At the simplest level, though, when we think of like metals bound together, we don't think of them as having formal bonds. Thought it said in here. So like the bonds in covalent bonds, as the book says, they're very directional. Shoot, that was a slide up here that I skipped. Highly directional, meaning that that bond energy, that sharing of electrons is happening in a specific direction. So it's between one atom and a specific other atom. In metals, though, the bonds are non-directional. They don't care which atoms that they're close to. And so that's why that non-directionality is what gives you things like, oh, there's those non-directional attractions. They can accommodate deformation because you smash it and it's not like this metal atom was really invested in this other metal atom. So I'm just now next to different metal atoms. So malleability, ductility, all those kinds of things. Also, conductivity, they conduct electricity because they're all sharing electrons in all directions. All right.